today to talk about one of the more undervalued topics in kinematics, and it's this idea of graphing the motion with a d versus t or v versus t or later an a versus t graph. A lot of people take these for granted and don't take the minimal time to really understand them so that when they see these graphs in the future, they can very quickly interpret them. So super important to really pay attention to this one. I promise you it's going to come back in the end, I promise. So let's start off with a basic idea. For our d versus t graph, well, take a look. Typically speaking, we're going to look at something kind of like this. If we have uniform motion, we're going to see a distance over time graph look like this. It's going to be a line, right? And we know that slope is rise over run, or rather a right angle triangle like that. And, well, since this is a distance versus time graph, if we do the rise over run, well, what do we get? Well, our rise is just our displacement, and our run is just our time. And we know that displacement divided by time is just our velocity. So if you have a d versus t graph, finding the slope is actually finding the velocity that is traveling. Now, this obviously assumes that it is moving in a constant velocity. You'll notice that there's no acceleration here. Otherwise, what would happen? Well, the displacement would change as a function of time. So we'll see one of those in a bit. Now, for velocity versus time graph, it's the same idea. If we take a look at a velocity versus time graph and we get something that looks just like this, and we have our run and we have our rise, well, our rise is just the change in velocity, and our run is just our time, which means change in velocity over time. We're dealing with the acceleration. So slope of the d versus t graph will give you our velocity. Slope of the v versus t graph will give you your acceleration. Now, there's one happy coincidence about these graphs, is if you take the area under the graph, you're going to find something useful. For example, when we have a velocity versus time graph, if we find the area underneath, so literally speaking, let's say we want to find from this point here, and we find this area under the graph, well, how do we get that area? Well, it's 1/2 the base times height. The base is time. The height is still our velocity. Velocity times time, well, that's just displacement. We get that from this equation up here. So if we find the area under the graph at any point on the graph, we actually are finding the displacement at that time. So that's pretty cool, and it's definitely worth understanding. You're going to be doing that a lot. Now, keep in mind, you may get some exotic shapes. You may get something that looks like this. And how do we find the area under the curve? Well, look, it's a rectangle and it's a triangle. So don't be afraid to break up the shape into whatever you can use. I'm not expecting you to know the equation to find the area under a rhombus or something like that. So it's always going to break down into a square, rectangle, triangle, something of that shape. So please be prepared. So let's take a look at something like this. Imagine a car at a stoplight. And then when the light turns green, it accelerates forward at a constant rate. What would a d versus t, v versus t, and an a versus t graph look like? Well, this is different than the examples I just used. Why? Because now we actually have some acceleration involved. So when I talk about sketch, it should look something like this. Very simple. You have d, you have t, you have v, you have t, you have a, you have t. And that's it. From this, you should be able to sketch decently what this looks like. Well, let's see. We are accelerating, okay, at a constant rate. Well, constant on a graph looks like what? Well, it looks like a horizontal line. You've seen this with constant velocity. So when you're dealing with a constant acceleration, it's going to be a flat line. So what is the v versus t graph going to look like? Well, we'll recall from the previous slide that the slope of a v versus t graph is going to give you the acceleration. So if there is no acceleration, the slope of a v versus t graph would just be 0. It would be a constant flat line, just like our acceleration versus time graph. But the fact that we have acceleration now means we'd better see something that is a straight line that looks like this. Why do we know it's sloped up and to the right? Well, because we're told that it is increasing at a constant rate. So this is positive, and it is positively increasing. So obviously if we're slowing down, which way is this line going to slope? Well, it's going to slope the opposite way. So something to consider. Now, distance versus time, well, what's happening? Well, I'm going to draw a quick diagram. If we had a car like this, and we started from rest, our first vector, if we break it down into a vector every second and then take the instantaneous velocity, what are we going to get? Well, at the first second, we're going to see a little tiny arrow. And the second, because we're accelerating, we're going to see something a little longer. Third second, we're going to see something even longer. Fourth, even longer. And so on and so forth. Why are the vectors increasing in size? Because it's accelerating. So how do we show a mathematical relationship that shows that it starts off quite slow and then starts to explode? Well, the answer is it's a nice, pretty curve like this. And you'll notice again, it starts off increasing slowly and then it starts to just jump up. And this is indicative of a object that is actually being accelerated. So any sort of curved graph in a d versus t indicates that there's acceleration in the system. So this is all accelerated motion. If we had uniform motion with a constant velocity, acceleration would be a line at 0, velocity would be a horizontal line, and distance would be a line on an angle, much like our v versus t graph here. So let's take a look at a different example here. Let's say we've got this blue car. And all I'm going to tell you is that this blue car is traveling at a constant velocity. Okay? Constant velocity for the first part of its trip. Let's say to here. Okay? So what would the graphs look like? Well, again, if we're going constant velocity, our acceleration is going to be that's a horrible straight line, but you get the idea. It is not actually below the line. It's at 0 because there is no acceleration. It's going the same speed. Well, what does our velocity versus time graph go? Well, it's going the same speed the whole time, so it is going to be a horizontal line. Well, what does that mean about displacement? That means it is going to be a nice line like this. Okay? So again, this is this idea of constant velocity. There's one step. Afterwards, let's say the car now accelerates to new v. Okay? And let's say that the a is constant, because I tell you, once you get into changing acceleration, where it changes over time, you get into a whole different ball of wax. We won't be dealing with that. So more than likely, your acceleration is going to be constant. If it changes, it will change to another constant instantaneously. So don't panic. What does our constant acceleration look like? Well, again, horizontal line, which means our velocity versus time is going to be sloped. Why do we know it's sloped? Because the slope of our velocity versus time graph gives us acceleration. And what does our displacement look like then? It is going to look like this. It starts off moving slow, and then it curves up. Now, are these to scale? Absolutely not. There is no scale involved here. We haven't imposed any sort of distances, any sort of times, right? So this graph here might make you think, well, he was already going at a velocity when he accelerated up. Sure. But at the same time, we're just talking about, relatively speaking, what do these graphs look like? So when you get into the more specific types of graphs, you're going to start to see some numbers on it. Then you're going to be able to impose some kind of scale and know exactly where it goes. Okay? So let's do one more, but this time we're going to say this. We're going to say we start at rest, and then we're going to speed up, and then we're going to go a constant v for a while, and then we're going to stop. Okay? Well, let's start off with the easy one. We start at rest and we speed up. What does our acceleration look like? Well, our acceleration is going to be a constant positive acceleration. Until when? Well, we end up at a constant velocity. Well, once we get up to this speed, what happens? Our acceleration goes down to 0, because now we're at constant velocity. Now, for those of you that are sticklers for specifics, can it instantaneously go from an acceleration positively to an acceleration of 0? Absolutely not. In the real world, there'd be a little bit of a curve involved there. It doesn't just instantaneously go from one acceleration to another. Again, we're just talking about the theory behind this, not the realism behind it. It's much uglier when you're dealing with the realistic viewpoint. For now, we're just trying to get the concept, so don't panic yet. Okay? Now, when we get up to our constant velocity, we stop. Now, let's say that when we stop, we slam the brakes. Okay, so we're stopping. Maybe we see a deer in the road. We're trying to get out of the way. What's going to happen to our acceleration? Well, our acceleration now is going to point against our motion, which means it's going to be negative. And because we're trying to decelerate in a hurry, it's going to be a large negative acceleration. Notice how this distance here and that distance there are two different values, right? What are we suggesting with this graph? We're suggesting that our acceleration up to our speed was slower than our deceleration down to no velocity at all. Okay? Now, if you get your acceleration versus time graph all figured out, the rest of it is cake. And what we're going to do is we're going to draw a dashed line right through all the graphs. So again, this is this idea of relatively speaking. Relative to our graph, we still have no scales, but we have the idea of what we're trying to get to. Okay? There are two major events that occur. We get up to our constant velocity and then we stop. So these dashed lines are showing these are different phases, okay? So when we're talking about our velocity versus time graph, we're trying to get up to a constant velocity, which means we're accelerating in this point until we get to our constant velocity. So notice again, this graph and that graph will match up exactly for the first, we'll call it third. Then what happens? Then our acceleration stops. Why? Because we are now at constant velocity. And then what happens? Well, we slam the brakes. And when we slam the brakes, what's going to happen? It's going to be a significant drop-off in velocity. So notice now the slope is going to be down and to the right. Well, that still means we have positive velocity, but it is slowing down. And the fact that the slope is more significant than the slope of the first third, that's suggesting that the slowdown is more severe. Now, I'm going to tickle up something here because I know it's probably bugging some of you now. And it's this idea of when we stop, this is actually another major point. So we only decelerate until we actually stop again. So that looks a little more specific. Okay, so we have our two graphs. Our acceleration looks good, our velocity matches up. Now we just have to make sure our distance versus time graph matches up again. So what do? In the first part, we are accelerating, which means we have this nice curve going. But what happens once we hit the constant velocity? Well, now we're going to end up with something that looks like a straight line. And sorry, I'm getting off the graph there. I just got too excited. And then we get right there. And what's going to happen? Well, we're going to slow down. And we're coming to a stop. Now, how do we represent that? Well, it's the other way. Instead of our displacement going at a constant rate, it's actually going to slow down like a curve. So you get something that looks like this. It almost plateaus out. And that, my friends, is what we're talking about. Okay, so it's a fairly severe curve, but again, we're talking relative, so that is the basic idea of what we're looking at. So speed up, constant, slow down. Speed up, constant, slow down. Speed up, constant, slow down. All three match up, we're good to go, my friends. That's about as tricky as you're ever going to see, is this idea where there's multiple events occurring and you have to take them all into account. So, you know the basics, you know something a little more advanced. Again, don't beat yourselves up over the idea that, oh, it doesn't match up exactly 100% correct. Just make sure you're able to explain physically what it is you're trying to say. So I think these graphs are fairly straightforward. Good luck, and we'll talk to you again.